Hello there. Let's go ahead and go through one of our lectures. Let's begin with 2.1, the idea of limits. So we're going to just develop this idea as the average velocity. As we go through the process, we're going to go through a formula that looks a lot like your slope. So just to recall, your slope is y2 minus y1 over x2 minus x1. Now, you should have seen something from maybe a college algebra course or maybe pre-calculus as the rate of change, which is a lot like your slope. So it says that if you're given a domain from, let's say, 1 to 2, that's supposed to be a bracket, then your rate of change would be f of 2 minus f of 1 divided by 2 minus 1, which is a lot like what your slope is, right? Okay, so keep this in mind as we go through this section. Let's go ahead and continue. Average velocity. Suppose you want to calculate your average velocity as you travel along a straight highway. If you pass milepost 100 at noon and milepost 130 at 12:30, you traveled 30 miles in half an hour. So your average velocity over this time interval is 30 over half an hour. It would be 60 miles per 1 hour. By contrast, even though your average velocity may be 60 miles per hour, it's almost certain that your instantaneous velocity, the speed indicated by your speedometer, varies from one moment to the next. All right, we're going to see this drawn out with this example. This is example 1. The rock is launched vertically upward from the ground with a speed of 96 feet per second. Neglecting air resistance, a well-known formula from physics states that the position of the rock after t seconds is given by the function s of t equals negative 16t squared plus 96t. The position s measured in feet, so that would be your x-axis, with s equaling 0 corresponding to the ground. Find the average velocity of the rock between each pair of times. All right, so for A, we're given time with t being 1 and t being 3. So if we want to use it as a rate of change, similarly to a slope, we see that at t1, our outcome, well, if we look at our graph, it's 80. And at t3, our outcome, 144. So I can find these rates of change by finding, in an easier sense, the slope of those points. So for A, our rate of change is 144 feet minus 80 feet divided by 3 seconds minus 1 second. So that we have 64 feet per 2 seconds. So that would simplify to be 32 feet per 1 second. And if your textbook, if you check it out, it gives you the formula to find the average at a certain point. Your velocity and your average velocity would be velocity to be s of t1 minus s of t0 divided by t1 minus t0. All right, we're going to do the same thing for B. For B, we see that at t1, our point is 80. We did that one already. And now at 2, we see our rate is 120. So I have 2 and 128. let's find our rate of change for those points. So we have 128 feet minus 80 feet divided by 2 minus 1. We get 48 feet per second, per 1 second. In example 1, we computed slopes of lines passing through 2 points on a curve. Any such line joining 2 points on a curve is called a secant line. The slope of a secant line denotes m per second is the position function example 1 on an interval t0 to t1. And we have this formula. So it's your slope per second. Instantaneous velocity. To compute the average velocity, we use the position of an object at 2 distinct points in time. How do we compute the instantaneous velocity at a single point in time? Such a deep question, because above we saw there were between 2 different points in time, right? It asked us to work between 1 and 3 and 1 and 2, but how about a single point? As illustrated in example 2, example 1, the instantaneous velocity at point t equals t0 is determined by computing the average velocity over intervals t0 or t0 and t1 that decrease in length. As t1 approaches t0, the average velocity typically approaches a unique number, which is the instantaneous velocity. This single number is called a limit. All right, let's continue with example 2. Estimate the instantaneous velocity of a rock from example 1. So same formula, same graph. But now I want it at a single point, 1. So how can I find this value at 1 if I don't have that range from 2 points, like from 1 to 2, or from 1 to 3, or from 1 to 4? How can I find a single point? Well, if you take a look at this chart from your text, we see, well, what if I create that range of t's to be a smaller number? So from 1 to 2, we did that one, we got 48. But what if I pick a small number that's smaller and closer to 1, such as 1.5? What about 1.1? What about 1.01? What if I keep picking points and I see that these numbers are getting closer and closer to a value? Do you see, as we pick a number that's smaller but closer to 1, we get it's approaching a number. We see that it's about approaching 64. And that is the instantaneous velocity. So let me write this down for you. We see it is approaching 64 feet per second. That's the instantaneous velocity. Okay, moving forward. Now, as we go through this part, it'll make a lot more sense once we develop this more, as we get closer to chapter 2. At the end of chapter 2, closer to chapter 3, we'll see this through a lot more and we'll understand it a bit better. But just to kind of get the idea of it, the slope of a tangent line. Several important conclusions allow from example Follow from example 1 and 2, each average velocity in the table below. So that was supposed to be that table. Correspond to slopes of a secant line on the graph of the position of the function. Just as the average velocity approaches a limit at t approaches 1, the slopes of the secant lines approach the same limit at t approaches 1. Specifically, as t approaches 1, two things happen. 1, the secant line approaches a unique line called the tangent line. 2, slopes of the secant line at the slope per second approach the slope of a tangent line at the point 1 and s of 1. Therefore, the slope of the tangent line is also expressed as a limit. So we saw our slope formula, but we can see it's also expressed as a limit, which we'll talk about in the next section. And we'll see by this picture that this limit is the same limit that defines the instantaneous velocity. Therefore, the instantaneous velocity at t equals 1 is the slope of the line tangent to the position of the curve at t equals 1. So all of here, don't let the m of per second throw you off. That's just your slopes, right? M equals slopes. So we're talking about slopes between points. And just as our captions say, the slopes of the secant line approach the slope of the tangent line. So we're talking at 1, which is this line right here at 64. Okay, I'll stop right here. We'll continue this idea at the end of chapter 2. And this is just getting us introduced to this idea of an average velocity and talking about limits and secant lines. Let's continue with section 2.2. Thank you.